Assalamu alaikum. This is lecture 7 of Information and Communication Technologies, and in this lecture we are going to continue our discussion about the number systems and the operation. So in this lecture we will augment our discussion about the numbers, and we will incorporate the representation of negative numbers. And after the representation of the negative numbers, we will perform some calculations or basic arithmetic operators on these binary numbers. There is another form of performing operation of the binary numbers, which is the calculation of numbers using logic gates, and these are often termed as Boolean algebra. Finally, we will conclude our discussion about the number systems using different number systems to represent number codes. So this is a comparison of different numbers from base 2 to base 16. So for each number you can see the base is provided in the first column. So it will start from 2 to 16. So as you can see, the 16 or hexadecimal number has a representation of 16 digits, and which are from 0 to 9, and for 10 to 15 we have representation of A to F. Similarly, for each lower number system we will have one less digit representation. So if we move to the decimal number system, we have 10 digits which are 0 to 9. So as you can see, once you reach to the limit of each number, the next number is 1, 0. So the most commonly used number system is the decimal number system by human, and computer use the binary number system. So if you count the numbers into the binary, you will start the counting from the 0. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this implies that we can apply the direct conversion method. That means every hexadecimal or decimal equivalent number system has the binary representation in 4-digit format. So as you can see, 0 is represented by 4 digits in 0 as well, and 15 is represented by 4 digits 1 subsequently. So in this way you can convert a hexadecimal number into a binary number directly by employing the 8 digits of binary number, and you can convert the binary number system to an octal number system using the 3-digit formula. So as you can see, if you divide the number into the groups of each having 4 digits into the binary number system, you can take the equivalent value into the hexadecimal number system. On the other hand, if you divide each number into the partitions containing 3 digits each, you can take the octal value of their representation. So go through these examples to understand more about direct conversion, and always keep this table into the mind while converting directly from hexadecimal to binary, and from octal to binary, and in reverse direction. So here is the representation to convert from octal to hexadecimal, but now you have known the direct conversion. So for each octal number you can take the binary equivalent in 3-digit format, and then convert this 3-digit format into 4-digit format, and we have two sets of 4-digit formats, and we convert these binary numbers into equivalent digits of hexadecimal. Therefore, our representation of octal is directly converted into the representation of hexadecimal, and you should try this example on your own. So here are some exercises for you to convert from one type to another and cross-check them whether or not this table represents correct versions of the numbers in a different format. So now we move our discussion to representation of negative numbers. So we have seen the positive number representation. How would you represent the negative numbers into the binary system? So well, there are three commonly used methods. So one is to use the signed magnitude, another is to use ones complement, and most commonly used is two's complement. So one way to represent the number into the negative number is to use the leftmost digit as a sign indication and treat the remaining bits for as if they were represented as unsigned integer. So the convention is that if the leftmost digit or the most significant bit is 0, the number is positive, and if it is 1, the number is negative. So for example, we have representation of two numbers. So in the first case, our most significant bit is 0. We have the representation of possible positive number, which is decimal 10. In the second case, we have representation of number, but in this case we have the most significant bit as 1. Therefore this is the negative representation of number, and again the number is same, 10. However, this representation leads to many problems, as this system is that it does not support the binary arithmetic, so which is what computers would normally do. So for example, if you find out the sum of these two values, 10 plus 10, you will result in 0. That means 10 plus minus 10 will cross out each other and you will get 0. But in this case, if you perform the calculation, you get the result in this value, which is the decimal representation of minus 20. Therefore, signed magnitude is not a useful method. So another method is to represent the number into ones complement to show its negative form. So to obtain the ones complement, you simply need to flip all the bits. For example, the bits represented here are 00001010 are reversed in each side. So each bit is converted from 1 to 0, and where the bit is 0 is converted to 1. So the negative representation will be like this for the same number. Now you can notice that the complement is equal to 245 in decimal, which is 255 minus 10. This is no coincidence. The complement of a number is the largest number represented by the number of bits available minus the number itself. So if we're using 8 bits here, that is the maximum number represented is 2 raised to power 8 minus 1, which is equal to 255. So the complement of 10 will be equal to 245. So in this way, the problem we found out in the previous method can be solved. So using the ones complement system to represent the negative numbers, we would have two zeros called plus 0 and negative 0. So let's say we use again the same method to perform 12 minus 12, and the result should be equal to 0. So we convert the numbers, negative number into the negative representation using 1's complement, our result is equal to minus 0. So this system partially solves the binary arithmetic problem because there are some special cases left. So let's say we perform 3 minus 2 and our result should be equal to 1. But once we convert minus 2 into the binary format, it is represented in this form, and when we calculate the resultant value is like this, which is equal to 256. So which is again problematic, but since we have only 8 bits to represent the number, the last bit will be discarded. That means the number will be equal to 0 in 8 bits. So this is not the answer we expected. So again, this technique is also not suitable. So the third form to represent the negative number is the 2's complement. 2's complement of a binary number is basically another number which, when added to the original, will make all the bits become zeros. So to find the 2's complement of any number, first find the 1's complement of that number and then add 1 to it. So let's take the previous example and we take the minus 12 value. Therefore, we convert the 12 into the binary and then take 1's complement. In the 1's complement, we just reverse the bits and then add decimal 1. So we will have representation of our negative 12 in 2's complement. Now let's say we add 12 with minus 5 to see if we have the same problem that we had when using the 1's complement system. So we had the simple representation of 12 and then we converted the 5 into 2's representation and then added those values to calculate the result, and finally we get the correct result. So this table shows the representation of different decimal numbers in signed magnitude, signed 1's complement and signed 2's complement. So as you can see, there are some similarities and there are some differences. For the positive side, the numbers are same for each representation. But for the negative side, you will see there is a variation in each format. So another problem we deal with the number is the overflow of the numbers. Overflow occurs when the value that we compute cannot fit into the number of bits we have allocated for the result. As you have seen in a previous slide that our result was 256 and we discarded the most significant bit because our result was in 9 bits. However, we had to use only 8 bits, therefore the 1 was the overflow. So for example, if each of the values stored using 8 bits, adding 127 to 3 would overflow. Once you add these values, the result is equal to 126, not 130. However, if we are not representing the negative numbers, the result would be correct. So the binary arithmetic is the calculation of binary numbers using different arithmetic operators. So it is similar to the arithmetic in decimal number systems, and you can perform addition, subtraction, multiplication and division on binary number systems similar to the decimal system. So for the addition, the first three cases are simple. When you add 0 and 0, the result is 0, 1 plus 0 result is 1, 0 plus 1 result is 1. However, when you add 1 plus 1, the result is 0 and you get the carry 1, which is further added to next value. On the subtraction, the three cases are same. 0 minus 0 is 0, 1 minus 0 is 0, 1 minus 1 is 0. However, if you take 0 minus 1, the result is 1 and carry is 1. This is the case when the when you take carry from the left column and left column remains 0. For the multiplication, the case is even simpler. 0 is multiplied by any other digit is 0 and you will have only one representation, which is 1 multiplied by 1. For division, you have the simpler cases. 0 divided by 1 is 0, 1 divided by 0 is not defined, and 0 divided by 0 is 0, and 1 divided by 0, sorry, 1 divided by 1 is equal to 1. So here is the implementation. As you can see, 1 plus 1 is 0 and you take 1 carry, and if you add it again, 1 plus 1 plus 1, which is again 1, and you take another carry which is represented in the last digit. Similarly, for minus or subtraction, you take carry from here to here, and it is 2 minus 1, which is 1, and for final you are left with 0. So here is the multiplication and the division cases. So here are some examples to try on your own. So this is the simple table for addition. As you can see, if you take 1 plus 1, you have 0 and 1 carry. So another way to perform operations on binary values is using Boolean algebra. Boolean algebra describes the relationship between the inputs and the outputs of digital circuit. It was presented by George Boole, an English mathematician, in 1854, which is based on the basic principles of algebra. Boolean algebra uses variables and operations, and Boolean variables has only two possible values, which are 0 or 1 or true or false. Basic logical operations are AND operation, OR operation, and NOT operation. So AND operation yields the true in case when both of the inputs are true. OR operation yields true in case when either or both of the inputs are true. NOT operation used to invert the value of its operand. So here is the working of the logical operations based on the input values. For the AND case, you have two inputs represented by 0, 0, 0, 1, 1, 0, and 1, 1. So as the definition suggests, it will be 0 for all cases except if both of the inputs are 1. So in the second case, we have a two input OR gate, and the definition stated it will be 1 if any of the input is 1, and if all of the or both of the inputs are 0, the result will be 0. In the NOT gate, the definition states that it will invert, that means it will convert 0 to 1 and 1 to 0. So you can use a combination of these gates to form different circuits. For example, a gate and connected with a NOT gate is usually called the NAND gate, which usually reverses the output of the AND gate. So as you can see, for the both of the inputs where the inputs are 1, the result is 0. On the other hand, if you add a NOT gate in front of a OR gate, it is a NOR gate. So in this case, the output will be 1 for the both 0 inputs. Another most commonly used gate is the exclusive OR gate, which is combination of and OR and NOT gates. So this will provide the output as 1 when you have the possibility of different inputs, and it will have the output 0 when you have the both inputs as same. So here are some more logical operations. So the first gate represents two input negative AND gates. So this is the inversion of inputs before applying the AND gate. Similarly, two input negative OR gate is again inversion of inputs and then application of OR gates. And exclusive NOR gate is application of exclusive OR gate and then inverting the output. So in this case, the output will be 1 when the both inputs are same. So the equivalent gates are provided down under for each of the examples. So the final discussion of this lecture is the representation of letters and symbols using different codes. So in many cases, computers use a standard library code to represent letters of alphabets, numerals, punctuation marks, and other special characters. These codes convert letters, numbers, special symbols into binary numbers. These are standard codes necessary for data transfer and some combinations of numbers to represent the same individual pieces of data. A widely used code is called ASCII, which stands for American Standard Code for Information Interchange. Some other popular codes are Extended ASCII, EBCDIC, and Unicode characters. So first we have the EBCDIC, which stands for Extended Binary Coded Decimal Interchange Code, which is 8-bit code to represent 256 different symbols. So these symbols include alphabets, numbers, and special symbols. So as you can see, you have representation from 0 to 255 for different kind of special symbols and letters, punctuation marks, and alphabets in small and capital letters. It is still used in IBM mainframes and mid-range computers. However, it is rarely used in personal. So another system is the ASCII, as discussed in previous slides. It stands for American Standard Code for Information Interchange, and it is most popular and widely used character set to represent English symbols. Initially, it was 7-bit code to represent 128 characters from 0 to 127. However, 33 are non-printable control characters, and now most of these are obsolete. Remaining 95 printable characters include space, which is invisible graphic character. So most commonly, the number 65 to 90 represent the capital letters, and from numbers 97 to 122 represent the small letters. Similarly, number 48 to 57 represent the digit from 0 to 9. Rest are some special symbols and some hidden or non-printable sequences. We have the extended ASCII version, which is 8-bit code that specifies the characters from values 128 to 255. So in this case, first 40 symbols represent pronunciation and special punctuation marks. Remaining are the graphics and other symbols, as you can see here. So the final code is the Unicode characters. Unicode Worldwide Character Standard provides up to 4-byte or 32 bits set of characters, and these can represent up to 4 billion characters or symbols, which are enough for every unique character and symbol in the world and even for Chinese, Korean, and Japanese language. Unicodes are used for special mathematical and scientific symbols. And again, the first 256 characters in Unicode are same as ASCII. The current version in May 2019 was 12.1, which contained about 137,000 characters from 150 different languages and scripts. So this concludes today's lecture, and if you want to explore more, please go through the recommended books or you can ask me any question. Thank you very much.